Okay, so this is test number 18. So this test is mainly based on hydrostatics, upthrust, and about hydrometer. So by taking this test, you can have an excellent understanding of those concepts. We'll move on to the first question. 0.1 cubic meter of water leaks to a boat floating in water. Okay, let's say so this is the cross section of the boat, and let's say the outside water level is to this level, and there's water leaked inside it. The volume of that water is 0.1 cubic meter, right? So this is the leaked amount of water. So you can see that this boat is floating, right? There's a really important concept here that you have to understand. In many times they have checked this, right? So you know that upthrust, since this is floating, upthrust is equal to weight. Weight of the boat. Weight of the boat is balanced by the upthrust. That's why this is floating, right? So what is the weight of the boat? Part of the weight of this total thing is only the boat. Another part is water. The total weight of this thing is the weight of this water and weight of the boat, right? So that is equal to the upthrust. That's why it floats. Then this upthrust should be equal to the weight of the boat plus weight of the leaked water. So you know that upthrust is equal to the weight of displaced liquid. Weight of displaced liquid, right? So this displaced liquid also can be, displaced liquid volume also can be think in two parts. This is one part, this is another part, right? So this is one is regarding V, this V, another one is regarding 0.1 cubic meters, right? So you can see this 0.1 cubic meter and water leaked weight, they are the same. Then what do you get? Weight of the boat is equal to another part related to the displaced. So this displaced liquid is related to what? The weight of the boat only, without this leakage water, right? So they say the mass of the boat is 100 kilogram. So the weight is 1000 kilogram for the boat, right? Only for the boat. So that amount of weight should be balanced by the upthrust created due to this displaced liquid. This displaced volume. So that is the first thing you have to understand. So whenever you have this amount of volume, that volume is always related to the empty boat or the vessel. I can draw it in another instance. Let's say a vessel is floating, and let's say there's a like water or something here. It should be water, right? Outside and inside. Then always you can see there's an additional excess. Additional volume immersed in the liquid. So this is additionally displaced. Why do always it is there? This volume creates the necessary upthrust to hold the empty vessel. This liquid weight is already balanced, right, by the water. This volume is always related to the empty vessel, or it can be a boat, it can be a ship, right? So that point you have to clearly understand, right? So you can see the uh, weight of the boat, so that should be 100 times 10 mg equals V rho g, upthrust created only by this. So here as V you substitute this volume, right? I think you understand that. So 100 equals V. What is V? That is what we need to find. Rho is the density of water, right? So V is equal to 0.1 cubic meters. So this volume also is 0.1 cubic meter. Here you have volume 0.1 cubic meter. Then the total immersed volume is 0.2 cubic meters, right? So that is the total. So this 0.0 cubic meter is displaced to balance out this amount of water, weight of this. Then this is displaced to balance out the weight of the boat, right? So that you have to clearly understand, right? Many times as MCQs in the exam they have checked whether you understand this concept clearly, right? So the answer should be second one. Second question: a vessel with uniform cross section floats on water. When water is added to the vessel, variation of height of water level inside the edge versus gap between water level inside and vessel and outside capital H is shown by. So this question as well is based on the previous theory, right? Theory, right? So there's water added, let's say, to this amount. Variation of height of water level inside the vessel. So let's say there's up to this level, there's water inside the vessel. Then capital H is what? This amount, right? Uh, the distance between inside water level and outside water level. That capital H. So in a graph, what they ask is variation between simple H and capital H. So to increase simple H, you need to add water, right? You need to add water so the water level inside increases, right? So what's the theory here? The main thing you have to understand is that this volume is always related to the weight of the vessel. Weight of the vessel is a constant, right? It doesn't change. Weight of the vessel does not change. So you can understand this H should be a constant. So you add in water, but in order to keep this H constant, you need to immerse. This system keeps immersing. As you add in water, keep in capital H constant. Why is capital H constant? Because weight of the vessel is constant. Empty vessel, right? Empty vessel means only the vessel without liquid. So when simple H increases, capital H does not increase. It remains constant. Understood? It remains constant, right? Even if this water level, so it keeps sinking. As you add in water, it keeps sinking. So that at the final moment, it will be like this. So outside water level is up to the brim of the vessel. Still, this capital H remains as capital H. Doesn't change. Now the simple H has increased, but this capital H does not change, right? This volume is always there in order to keep the weight of the vessel in equilibrium. Right. Third one, a solid object made of material with density 650 kilograms per cubic meter floats in liquid with density 800 kilograms per cubic meter. Okay. So we have this solid object. So material, the density is 650. Then there's the liquid. It has 800 kilograms per cubic meter. Those are the densities. Fraction of immersed volume of the object is. So let's say immersed volume is V dash, and let's say total volume is capital V. Immersed volume is V dash, right? Or the displaced liquid volume. Right. So what they ask is fraction, immersed fraction of volume. So how do you do that? You can understand this object obviously floats, right? If it is a solid object and it has less density compared to the liquid, it floats. So if it floats, you can say upthrust actin is equal to the total weight. So upthrust always you can use V rho G equals mg, then you can get rid of G. So you get V rho equals m, right? So you have to clearly understand this volume, this density, and this mass. So what are we talking about, right? So V is displaced volume. You have to clearly define that. V is the displaced volume, not the total volume. So the displaced liquid volume is V dash. This is what density? This is the density of liquid. You don't have to memorize this, right? If you clearly understand what upthrust means by the fundamentals, right? So if I recall you, what's the upthrust? Upthrust is always equal to the weight of the displaced liquid. Weight of the displaced liquid. So obviously this V rho, this should be weight of the liquid, right? So this density should be density of the liquid, not the density of the object. Okay? Right. So what's the liquid density? 800. Then mass. Mass of the object. So clearly have to understand whether it is object or liquid, fluid. So mass of the object. So how do you get the mass of the object? Density of the object is given, right? So density times volume, right? Think in terms of units. Cubic meters cancel, so you have to multiply volume. Some students don't understand these as well. They don't even know how to convert that mass, how to find the mass if volume and density is given. So they at the primary level, that's why I'm explaining this. Density times volume is what you when you get mass. So this is object, right? So this density should be density of the object. So 650 times volume of the object, not displaced volume, right? Volume of the object, that is what we get that as V, right? So we have everything we need to get the fraction of immersed volume. So that is V dash divided by V is equal to 650 divided by 800. Divided by 5, 13, 16. 13 divided by 16. Right? So that is the second answer there. Okay? So if they have asked a percentage, all you have to do is just multiply this by 100%. Right? Fourth question. Fraction of immersed volume of a plastic piece is 5/6. If density of liquid is 800, density of plastic is, let's say, sigma. So there's two volumes, volume of the object, volume immersed or the displaced volume, right? Immersed volume fraction is given as 5/6. So the same thing, this is a similar question to the previous one. So you can see upthrust is equal to mg. So upthrust is v rho g, right? G cancels off, so you get the same equation, v rho equals mass. So this v is displaced volume. Let's say that displaced volume is v dash. Rho is 800, then mass. Mass equals density times volume. Okay. Density of the object, that is what you need to find, sigma times density of the object. This v is not displaced volume, right? This is density of the volume of the object. So I can take it as let's say v, capital V, right? Again, then take it to this side, equals sigma divided by 800. So the fraction immersed is given. So this is v dash divided by v, it is given as 5/6, right? Now only unknown is sigma, then you can find that. So what do you have to do? 800 times 5, 44,000 divided by 60, right? 40 times 100, 4,000 divided by 60. Divided by 2, 2000 divided by 3, so 66666. So if you round it off, it becomes 0.7 kg per cubic meter. So this is sigma, right? So this is the density of the object. Right. Fifth question. Two objects, x and y, float in water. Okay, now we have two objects, right? One is x, another one is y. They don't say that the volumes are equal. So all they say is, let's say total volume of the object. Here I will take it as V1. So you can see half of that is immersed at x, right? Let's say for y, 4/5 of the volume is immersed. So this much, let's say V2 is immersed, right? So this is for y. 4/5 of the volume of the second object is immersed. So they have given those. Then there is a ratio of relative densities between x and y objects. Let's say the density here is d1, density here is d2. I mean actual densities, right? Not, I mean real density, absolute densities, let's say d1 and d2. So there are two cases. So I'll just apply equations. So for this one you can apply v rho g equals mg. So it is, if you get rid of g, it becomes v rho equals m, right? So here you can substitute for v, immersed volume, that is v1 divided by 2 times rho. I'll say d1, density of that. No, it should be density of the liquid, right? So I'll take it as rho, density of the liquid as rho. Yeah, they say it is water, so I'll just take it as rho. Then mass of the object. So the total volume of the object times density of the object, that is d1, right? So we have this equation. Then if you want, you can get rid of v1, then you can get this equation, rho divided by 2 equals d1. Then go for this. So for that also you can apply v rho equals m. So here displaced volume is 4v2 divided by 5. Rho is density of the liquid. I took it as water, right? It is the same liquid. Mass of the object. I can take it as v2 times density of the object. This object density is d2, right? For this one also I can get rid of v2. So you have d2 equals 4 rho divided by 5. Okay. Then they are asking about a ratio between D1 and D2. So for D1 you can get rho divided by 2. For D2 you can get 4 rho divided by 5. So you know that you can get rid of rho. Then I'll just multiply both values by 10. You can do that in ratios, right? So just you are doing it in your head, right? You don't have to write it. Multiply this by 10, this becomes 5. This by 10, this becomes 8. Right? 2 times 2, 4, 8. You learn these in O levels, right? How to do these calculations. If you still cannot do this, it is really disappointing, right? Now you have been doing for a long time. So these simple calculations, you should know this by now. Right. So this is 5 to 5 is to 8. So this is the ratio between these densities. So you know that for the relative density also, you just have to divide by 1000. Even if you divide by 1000, you still get the same ratio, right? Because it is a constant. Okay, so the ratio is 5 is to 8. Third one is the answer. Right. Sixth question. A wooden block with mass capital M floats on water, soil 1/4 of its volume is above the water level. Right. So we have a wooden block. Then 1/4 is above the water level. So let's say total volume is V. So VO4 is above the water level. 3 VO4 is immersed. Right. If a simple M mass is placed on top of it, the wooden block just sinks fully. Okay. So the second case, you place a simple M object, simple M mass on here. Then what happens is this fully sinks. There are two ways you can do this, right? For this one you can write U equals mg and do the force balance. For this case just apply U equals mg. Then compare or solve those two equations and get the answer, right? So that is the one way. Everyone can understand that one, right? But this is an MCQ, so what they understand, what they want you to do is in a shortcut method, right? If you really understand upthrust, you have to understand that displaced liquid related to this volume is equal to weight of this extra mass. Got it? Understood? Then this question will get really easy if you understand that. So, at the second case, what is the difference? What is the increased amount of upthrust? So, this is the usual equation, U equals mg. But I can get delta U equals delta mg, right? So, this is increased upthrust equals increased mass times g. If you want, you can take g here because it's a constant, it doesn't change. So what is this? So whenever you get a question, you can put a delta there, but you have to understand the variable, right? At the two cases. So the variable is upthrust here and the increased additional mass. When you compare these two, then you can apply this for any equation, right? Doesn't matter. So those who use these will solve these questions really quickly, right? If one student spends like 5 minutes, someone who uses these will spend like 20 seconds or 30 seconds to solve this, right? So that's what causes the difference between an A student and a CESF student, right? Right. So the thing is, they know how to work around those to quickly get the correct answer, right? So that doesn't comes easily. It comes with hard work, right? With practice. Okay. So increase of upthrust. What is that? It is related to this amount, right? This is the immersed, further immersed amount at the second case. So that is V over 4. Density of liquid, is it given? It is, they have given that as water. So I'll say, so this is V rho G, right? Rho, only rho is enough. V rho equals delta M. So delta M is what? I just got rid of G, right? From both sides you can get rid of G. So this is V rho equals delta M is simple M, right? So you can get simple M is equal to this much. Then, so for this case also you can apply the equation. For the whole system, if I apply that, so you know that V rho is equal to M, right? So the immersed amount is 3V over 4, rho is density of water. This mass is the mass of the whole object, right? So that is given as capital M. That is given as capital M, right? So when you compare these two, you can see that 1000 and V over 4, what's the value of that? It is simple M, right? So 3M equals capital M. So the simple M is equal to capital M over 3. So that is the weight to be placed on here. So this fully sinks, just fully sinks. So the answer should be first one there. So there are many ways you can get the answer, but you have to make sure that the time you are consuming, especially for an MCQ, is a short time, right? So anyone can get the answer for an MCQ if they are given an unlimited time. The trick is, if you know physics, I mean, if you have really practiced these questions, you need to be able to go for the answer within a short time, right? Okay, next one, 7th. A metal cube made of material with density 1800 has a hole inside it. If 3/4 of its volume is immersed in water, right? So this is the total volume. 3/4 is immersed. Volume fraction of the whole is, right? So let's say the this total volume is V, and let's say for the whole it has a V dash volume. So what they ask is a fraction of the volume of the whole, right? This is a hollow cube, right? So for this as well, just apply upthrust equals weight. Floats, right? Floating. So V rho equals mass. So what is this V? Immersed volume. Immersed volume is 3V over 4. Rho, density of the liquid, right? It is water. They have given it as water, so 1000. Then the mass of the object. So when you find the mass, you need to find the solid volume. This volume, right? You are getting this volume. So that volume is total volume of the cube minus the volume of the whole, right? Total volume minus volume of the whole. Then you get the volume that contains solid times density. that is 1800. Okay, right. Divide by 1000 both sides. Then 3v over 4 equals v minus v dash. V dash to the other side, take this to other side, then it becomes v minus 3v over 4, which is v over 4. Then v dash over v, cross multiply, equals 1 over 4. Sorry, there's 1.8 as well, right? Yeah, there's a miscalculation here. So if you want, you can make it a decimal. I think, let's see, 0.75v equals 1.8v minus 1.8v dash. Get this to the other side, 1.8v dash equals 1.8v minus 0.75v. 5, 7 minus 7, 0, 1. So here you have 1.05v equals 1.8v dash. Then v dash equal, or v equals 1.05 divided by 1.8. 105 divided by 180. Just multiply by 100. 2, 1, 3, 6, 7, 9. If you divide, no, sorry, 7, 3, right? If you divide by 3, you get 7. Divide by 3, you get 12. 7 over 12. It's better if you just kept the fractions only, then the calculations won't get this complicated. Anyway, the answer there is 7 over 12, right? Right, 8th question. An object with volume V, which is made of a material with density D, floats inside two immiscible liquids with densities D1 and D2. Volume of the object that is in liquid with density D1 is. And further they have given that D2 is less than D1. Okay, so we have the object with volume V, then two immiscible liquids, right? They don't mix, with densities D1 and D2. So D1 should be at the bottom, then you have D2. Volume of the object that is in liquid with density D1. So here at the D1, so what they ask is volume here. Let's say that is V1, right? Right. The volume of the total object is given as V. And you can see this volume is V minus V1. V minus V1, this volume. Right. So for this also it is U equals mg, right? Since there are two liquids here, you have to consider the upthrust regarding this liquid plus this liquid. So you can see U1 plus let's say U2 equals mg. So for U1 you are considering this part. So the volume is V1, density liquid D1 G plus U2, this part. Volume is V minus V1, right? V minus V1. Density is D2 G equals mg. This m, you can write it as, it is a mass of the object, right? So the density of the object is given as simple d. Then the volume of the object, we know that is capital V, right? Times g. Then this g you can get rid of that G. So what they ask is V1. So you need to subject V1 from this. So here you have V1 D1 plus, if you multiply by D2, you get V D2 minus V1 D2 equals dV. You just have to find V1, right? Okay, from these two terms, I'll take V1 out. You get D minus D2. D minus D2 equals to, just take this term to the other side. So you have V D minus V D2. Just subject V1. Take V out. D minus D2 divided by D. Where did we go wrong? D minus D2. This is V1, right? V1, D1 minus D2. So this is D1 minus D2, right? So this is the immersed volume inside the liquid one, inside this one, right? So in all these cases, you just have to apply U equals mg. But if there are several liquids, you have to get upthrust regarding each liquid, right? Then add all those, so that the sum of those upthrust is going to be equal to the weight of the object, given that the object is floating. Right, ninth question. A wood block with relative density 0.5 attached by a string to a concrete block with relative density 2.5 floats but fully immersed inside water. Mass ratio between wooden block and concrete block is. Okay. So relative density they have given 0.5 for the wooden block. And there's concrete block which has 2.5. So this is less than density of water, this is more than density of water. So this is trying to sink, this is trying to float. Anyway, the whole system remains at rest, right, in equilibrium. So this is the liquid. So what they ask is mass ratio between wooden block and concrete block. So this is the wooden block, let's say M1, concrete block M2. So they are asking about a mass ratio, right? So it's better to get all those equations in terms of mass, because they are asking about a mass ratio, right? Okay. So for this, you have to get the equation for the equilibrium. So you know there's tension here, but if you consider this to be a one system, these tensions becomes internal forces. So you don't have to deal with tensions there. On this one, there's a U1 of upthrust. Here as well, there's a U2 of upthrust. And then it also has weights, M2G, here M1G. So these four forces are the only forces here, right? These tensions, they are internal forces. If you want, you can find the tensions, right, by considering only part of the system. But they don't ask that. So for the equilibrium, if you write the equations, so upward it is U1 plus U2, downwards it is M1G minus M2G. The whole thing is equal to 0. So you can say U1 plus U2 equals M1G plus M2G. So U1, how do you write U1? Let's say that is V1 rho G plus V2 rho G. This is just for explanation, right? If you want, you can at once write the do the substitution. This is just for explanation, okay? So V2 rho is the density of water, okay? Both same. So you have M1G plus M2G. You can see then get rid of G, right? What do we end up with? V1 rho plus V2 rho equals M1 plus M2. Remember that we have to find the ratio between masses, right? So this V1, how do you write V1? Volume of this object. You need to write that in terms of the mass. So this mass, this volume is equal to what? Mass divided by density, okay? Density of the object. Mass divided by density is volume. If you have doubts, check the units, right? Kilograms. Here you have kilograms per cubic meters. Kilogram cancels off, cubic meters goes up. So you get volume. So instead of this rho 1, you can write mass of that divided by the density. Then density is given as 0.5. You can substitute in terms of relative density, okay? Because here you have a fraction. But you need to be careful there, right? 0.5. The thing is, you can consider this in terms of grams per cubic centimeter. Later you can convert that. For now, let's consider that 0.5 is in grams per cubic centimeter, right? So just remember that these, so all the terms are in grams per cubic centimeter, right? Okay, so grams per cubic centimeter means this rho also is 1. This is the density of water is 1 plus V2. V2 is mass of this object. M2 divided by density of that object, 2.5 times density of the liquid, that is 1. Water, right? Equals M1 plus M2. Right. Here, this is 0.5. M1 divided by 0.5. M1 divided by 1 over 2. So it goes up, it becomes 2m1 plus, this you can write it as 5 over 2. 2 goes up, 5 at the denominator, equals m1 plus m2. Then subtract m1 equals 5, 3, m2. Okay. Then cross multiply, m1 over m2 is equal to 3 over 5. It is equal to 3 over 5. So the ratio should be 3:5, right? So that is the mass ratio between wooden block and the concrete block. So you can see that all the terms are written. Finally, we got those terms in mass. So at once you should be able to do that, right? With density. Involving density, convert something into a mass, to a volume, without thinking too much. You should be able to do those, right? Otherwise, these are hard. Otherwise, right? Right. 10th. When the weight of a throne is measured in air using a spring balance, it is 7.84 Newton. So using a spring balance, right? So let's say this is the throne, right? Not throne. So so this is mg. So in air it is equal to the actual weight. So this mg is 7.84 Newton. When it is measured fully immersed in water, then what do? You do the same but now the crown is, it is a crown, right? There's a mistake there. Crown is fully immersed in water. Fully immersed in water. Then what happens is, now there's a upthrust acting on the crown. Now they say the reading is 6.86 Newton, right? So you can see the reduction of the reading, right? From 7.84 to 6.86. So what causes this reduction? There's upthrust causing it on the crown because this is immersed, right? So the reading decreases to 6.86 Newton, right? So you can see the difference of these two. The difference is caused by the upthrust. So the upthrust should be equal to the difference. That is 7.84 Newton minus 6.86, right? So 4 minus 6, 14, 6, 8, 7, 17, 8, 9. So you get 6 minus 6, 0. So you have 0.98 Newton. So you can see now the upthrust acting on the crown is 0.98. Okay. So the A is correct. Upthrust when crown is in water is 0.98. That is correct. Density of material that the crown made is 8,000 kilograms per cubic meter. So to find the density of material, crown material, we need to go for a equation. So we already know the upthrust. So you know upthrust is equal to V rho G. So instead of upthrust, you can write 0.98. It is known, right? Then the volume. How do you write the volume of the crown? You can write the volume of the crown by dividing mass of the volume by density of crown material. So mass of the crown, that is, this is the real weight, right? It is, I mean, real weight means just regarding the mass. So the mass should be 0.78. So just 84. Just divide by 10. 0.784 kilogram. Divide by 10. So mass divided by density of the crown material times rho. Rho is for the liquid. It is water. So you know for the water it is 1000, right? Then you have G. G means 10. So the only unknown is this sigma, which is the density of the crown material. Okay. Just take this to this side. So sigma equals, if you want, you can multiply this. So it becomes 784 and 1000 0.98, right? Let's divide this by 2, 4, 9, 3, 9, 2, 0. I think you can divide this by 7, right? 0.07. Divide this by 7. You get 5, 7, 0. Right? 570. Should divide, no, 5, 6, right? 560. Okay, so we have 560 divided by 0.07. You know 560 means 8. 8 times 7, 80 divided by 0.01. This is 100th. So it goes up. It becomes 8,000 kilograms per cubic meter. Right? 80 times 100. 8,000 kilograms per cubic meter. So the B also is correct. So A is correct. B is correct. Then C. Crown is not made of gold. You know, the density of gold is, they have given as 90,000, 19,000. But the density we got from the calculations is 8,000. So it is way less, right? So this cannot be gold. It is not made of gold, right? So it is a fake gold crown, right? So there's a story behind this as well. I think you may have heard the story, right? So all are true, right? A, B, and C, all are true. Right. 11th question. If the floating object is to be in stable equilibrium, so they're asking about the positions of center of gravity of the object and center of buoyancy, right? Center of buoyancy. Okay. So let's take an object. I'll just give you a quick reminder of what center of buoyancy is. So if you have an object that is fully immersed, and if, let's say, uniform, like a spherical shape, and uniform object, so the center of gravity is right at the center, right? Center of buoyancy is center of gravity of displaced liquid. Displaced liquid volume. So the displaced liquid volume is also this much. For that one, center of buoyancy also should be here, at the same place. Another thing, let's say there's an object like this, right? So for the center of gravity, it could be somewhere here for the object. But the center of buoyancy is the center of displaced liquid. This is the displaced liquid. So it is below now, B. Okay. So they are asking about stability of the object. What is the stability? I mean, what is the equilibrium type? Whether it is stable, unstable, or neutral, right? Actually, they are asking about stable equilibrium, right? Right. I'll just quickly remind you stability. So here upthrust is acting on this point. Weight also is acting on the same point. So even if you rotate this and release it, it will remain like that. Doesn't change. If you get this object and let's say you tilt that object, what happens is G comes here when you tilt it, right? So that is how you check the equilibrium. G comes here, B comes here. So G downwards, B upthrust upwards. So you can see this creates a couple, right? That couple rotates the object. So you can see in this case it is unstable, right? The original position cannot be required. Like if you tilt it a bit, it just flips, right? So that equilibrium position is unstable. Then if you think about an object, so for that object, G is below, B is above, right? So what happens when you tilt that? B comes here, G comes here. So G is acting to this side, upthrust is acting upwards. So when you tilt it, let's say to this side, there's a counter torque acting on there. So the original position of the object is acquired, right? Due to this counter couple. So this is the stability. So in order for that to happen, center of gravity should be below the center of buoyancy or the point of buoyancy, right? So this is the stable equilibrium. Okay. So I explained this using forces, using energy as well. You can explain that. There are theory we have learned earlier. So the thing is, in order to have the stable equilibrium, the center of gravity should be below the center of buoyancy. So what's the answer? Second one, right? Point of buoyancy should be directly above. Right. 12th question. Consider the expressions about a hydrometer. Upthrust is higher when it floats on salty water than on just water. So let's consider the first expression. So let's say you have this hydrometer, right? So you know hydrometer is always, if you need to use the hydrometer, weight of the hydrometer should be equal to the upthrust. Otherwise hydrometer would sink, right? Then you cannot get readings. So they always, hydrometer should be floating on water, right? So you can get the reading from here, right? So you know the upthrust, and then you have weight of the hydrometer. In order to get the reading, you should be equal to the mg. Weight and the upthrust should be equal. So let's say you immerse this in, like, here water, then in salty water. Does the upthrust change? No. Why? Because upthrust is always going to be equal to the weight of the hydrometer, right? Regardless of the liquid you immerse the hydrometer. If the hydrometer is to be remain in equilibrium, always upthrust acting on the hydrometer is equal to the weight, right? So it is true that U means V rho G. You can understand that for different liquids, this V and rho changes. But that change happened in order to keep this whole thing a constant, because it always should be equal to the weight of the hydrometer, regardless of the liquid you are putting it in, right? For the same hydrometer, right? Right. Then they say something about second one. So A is wrong, right? So second one is calibration is uniform. Calibration means here, right? So I'm not going to write the whole equation here. If you want to write the whole equation, you can take this volume to be like, let's say V dash, and this immersed volume, let's say immersed height is simple h, and the cross section here is capital A, right? Then you have mg, that is the weight of the hydrometer, is equal to upthrust. So the upthrust is V dash rho means density of the liquid, right? Which is to be measured. V dash rho G plus this much. What's this volume? Cross sections times H times same density times G. Get rid of G, right? Then I'll subject rho. You have V dash plus H equals M. So rho is equal to what? M divided by V dash plus AH, right? So you can clearly see that when you think about a combination between density of the liquid and immersed height, that is simple H of this stem, right? Immersed height of the stem. That is where the calibration is done. You can clearly see it is not in this form, right? Y equals mx plus c. It is not clearly in this form. So this has kind of like an inverse combination. It is not inversely proportional, but there's a inverse combination, because if H increases, meaning if this further sinks, the density should be lower. So it is obvious, right? When you put this in a liquid with lower density, this further immerses. So the reading increases. But you can clearly see this is not a linear scale, right? Not a linear calibration, right? So for this one, these values changes as it goes up, right? It increases, density keeps increasing. So the gaps are not equal. right, for the hydrometer. So B also is not correct. Then C, tube with calibration, meaning this stem is designed thin. It is thin, right, to increase the sensitivity. So what is the sensitivity? So sensitivity of a measuring instrument is determined by when you change the quantity physical quantity to be measured, what's the response of that measuring instrument. So if this has a large response, large reading for a small change of the density, then we say that hydrometer has a higher sensitivity. So it is sensitive, right? If the response is higher, not response time, okay, response. If the response is higher for a given change, then we say that is a more sensitive. So here the response means this H, right? So you can see if A make it thin, in order to get that immersed volume, it has to dramatically increase, right, when you decrease A. So actually that is why you make this thin. It is the only reason, right, in order to increase the sensitivity. So higher the sensitivity, better. Okay. So there only C is true, A and B not true. Right. 13th question. 1/5 of volume of a hydrometer is above the oil level when it floats. Density of oil is 0.9. Density means relative density. You understand that? If hydrometer floats in a liquid, 1/10 of its volume is above liquid level. The density of the liquid is here density means liquid. I mean not liquid. Density of means relative density, right? So you can identify that by the units because it's unitless, right? So you have this hydrometer immersed in a liquid and the density is 0.9. So you know this is floating, so mg is equal to v rho g, so mass is v rho. So I'm going to use this equation. If you have this relative density of the liquid, 1/5 of the volume of the hydrometer is above, right? So 4/5 is immersed, 1/5 is above, right? 4/5 is immersed. So that is for the oil, right? Then you have another liquid, same hydrometer, 1/10 is above. So it has immersed, right? Further. So 9/10 of the total volume is below the liquid level. Let's say for that one it is D, density, right? So when you think about this case and this case, we are using the same hydrometer. So the mass of the hydrometer is the same, right? So you can understand for this first case, if you write, let's say immersed volume is V, let's say density is rho 1. For the second case also it is V2 rho 2. This product does not change, right? You can understand that. Mass does not change, so this product also does not change. Right. So here V1 is what? 4V over 5. Rho 1 is 0.9. Okay. Does not matter the units, right? Because you can, if you want, you can think like grams per cubic centimeter. Then you have to according to work there, right? Don't multiply by 1000 all the time, right? It complicates things. Right. If necessary, you have to, but in most cases, you don't have to, right? To multiply by 1000. Okay. V2, it is 9V over 10 times rho. that is D, right? So what they ask is this D. Okay, V cancels off, 1, 2, this comes here, 8, 1, 0.1. So what is D? D is equal to 0.8. That's the relative density of other liquid. So you can see here the density is 0.9, here the density is less. So the hydrometer has immersed further, right? You have to think those as well, right? So the answer is third one there. Right, 14th question. Upthrust acting on a wooden block floating on water vessel inside lift moving at 2 meters per second is 2 Newton. So let's say there's this lift, there's a water vessel, then there's a wooden block, right, floating, and they say upthrust is 2 Newton acting on the wooden block. Upthrust acting on the object when the lift moves upwards at 2 meters per square second. So initially it is 2 meters per second, right? You know that upthrust is equal to 2 Newton in this case. If it is moving at constant speed. So you know when you apply F equals ma, whether it is constant speed or at rest, you get the same force. But if you have an acceleration, for this case, you know upthrust increases. There's an equation to get that, U equals V rho G plus A, right? G plus A or G minus A. If you want, you can use that equation if you know that. Or else you can use F equals ma to find the new upthrust. There are two ways. I'll just, so you just have to substitute here, right? I'll just show you how to apply F equals ma for this case when it accelerates. Okay. Now the upthrust is like U dash, right? U dash, it has increase, change, and the weight. So U dash upwards minus weight. Weight does not change, right? Weight is, you know that weight of the object here is mg, that also is equal to 2 Newton. Here also it is 2 Newton. Weight of the object does not change. Is equal to ma. So how do you get the mass? Mass of the object. So the mass of the object is equal to 0.2 actually. Why? Mg is equal to 2, so mass is equal to divide by 10. 0.2 kilogram mass times acceleration. Now the acceleration is 2, right? So you can see U dash equals 2 plus 0.4. 2.4 Newton. Get it? This is the upthrust. Or else you can simply use this equation. V rho G plus C. Right? So here V rho means what? V rho can be found using this one. Okay? You know that immersed volume V rho G is equal to mg, V rho is equal to m. So you know V rho is equal to 0.2 here. Right? Then you have here 10 plus 2. 2 plus 0.4. So you get the same mass, 2.4 Newton. If the acceleration downwards, you have to get G minus A. Since it is upwards here, it is G plus A. Right? 2.4 Newtons. So the value is fourth one there. Right. 15th question. So for the 15th question, I have included 2024 LL question, right? Okay. A small solid sphere made of a material having density beta is released from rest at a depth capital H. The density of the object is beta. Below the surface of a water tank, the density of water is rho. So they have given rho is greater than beta, right? So this is trying to move upwards because this is trying to float. This density is less. What is the maximum height that the sphere will rise from the surface? Neglect all the viscous and surface tension of water. About viscous and surface tensions, you learn them in at properties of matter. That's the 10th unit, right? You don't have to consider, it is not necessary here. Okay, so what happens here? Upthrust. So these are the forces acting on this object. Upthrust minus mg and mg, right? So what happens, this upthrust is larger. That's why it is start to move upwards, right? Let's say acceleration is simple A. It starts at rest. So you have to include all these in terms of the given values, right? This u and mg, we applied that, right? So here what happens is this comes here, accelerate, having an acceleration, then it gains a velocity here. So if it has a velocity here and there's no surface tension, if there's a surface tension, that there's an energy loss here, but there's no energy losses because they say neglect the surface tensions and viscous forces, right? So you can consider that you can just apply the energy equations, or you can apply motion equations simply. After that, so here it has acceleration, let's say simple A, then due to this velocity, it starts to go up as well, right? Starts to go up, and here the velocity becomes 0. So what they ask is maximum height that the sphere will rise from the surface. So let's say that maximum height is simple h. Okay. So from here to here, different acceleration. From here to here, it is moving under gravity, right? So you can see you have to just apply F equals ma and motion equations, and you have to find this simple h. Okay. So I'll first apply to this case. I first need to find the acceleration. So what do? You just have to apply F equals ma. Force upwards u, downwards mg equals ma. Right. So this u is what? V rho g minus mg equals ma. If you want, you can write each of these terms in mass or in terms of volume. I think it is easy to just put mass here because you only have to convert it here, right? So the volume is equal to what? Mass divided by density. So whole object is immersed, right? So mass of the object, let's say simple m. This is also simple m, right? These are mass of the object. I'm applying the equation to mass to the object, right? So here mass of the object divided by density of the object. It is given as beta. Are they relative densities or just densities? Yeah, just densities, right? Okay. So mass divided by density times rho, that is the liquid, G minus mg equals ma. Okay. Now you can get rid of m, simple m, mass of the object. So what do you get? You get rho g divided by beta, rho g divided by beta minus g equals a. take G out, you get rho divided by beta minus 1. This is equal to simple A. Right? Now we found the acceleration in terms of rho, beta and G. Okay. Anyway, the final answer should be in terms of rho, beta and capital H. Okay. Right. Now we have this one. Then I'm going to apply a motion equation from here to here. So the beta one is, there's no time involved. So the beta one is v squared, right? V squared, u squared, 2as. So the final velocity, it is here. So I'm applying from 1 to 2. This is, let's say 3. Final velocity is 0. Initial velocity at rest. Sorry, final velocity is v, right? It gets a velocity from here to here. It gains a velocity. Initial velocity is 0. 2 acceleration times simple S means capital H from here to here. Okay? Right. So I'll get a equation for 2H times A in terms of this one. So simple A means G rho divided by beta minus 1. So this is V squared, right? Okay. Then what you need to find is simple H. In order to find that, I'll just apply equations from 2 to 3. Motion equations. V squared, u squared plus 2as. So final velocity, that is 0. Initial velocity, meaning at 2, right? From 2 to 3. It is v. Later, if you want, you can substitute it from here. So this v, right? V squared plus 2. Gravitational acceleration downwards, so minus g times simple h. This simple h is what you need to find. Take this to the other side, so 2gh equals v squared. We already have a term for v squared, this term. So that is 2hg rho divided by beta minus 1. So this 2g cancels off, so h is equal to capital H rho divided by beta minus 1. Okay? Rho divided by beta minus 1 times capital H. So that's the answer there. So the answer is fifth one. Okay. You might think this is a complicated question. No, right? This is a normal motion equation question. Only difference is there's a liquid involved and upthrust involved. The rest is just you just have to apply motion equations, right? So if you clearly understand those, then this is not a complicated question. It takes, to be true, this takes some time, right? At least like 1 minute and a half. So this is exam question. So it takes like, for a better one, very skilled student, it will take just 1 minute, right? But you have to you need to be able to correctly understand this and correctly apply these equations. At the end, you will get the answer, right? But that comes with practice, okay? Right. So I'll wind up here. So that's all the questions regarding hydrostatics. So the next test will be on hydrodynamics, right? So there will be one test to cover hydrodynamics part.